In this lesson, we're going to learn another parent function called an exponential function in which the input x is actually in the exponent. So I'd like to compare this new exponential function with a couple of functions that we're already familiar with. For instance, f of x equals 2x, which is a linear function, and f of x, or g of x equals x squared, which is a quadratic function. So let's take a look at the linear function first, and afterwards we'll see the quadratic and the exponential. So if we just take a few inputs and find the corresponding outputs for the linear function, remember that all this function is telling us to do is to take the input and multiply it by 2, which is why you can see that every output is just 2 times the original input. So if you were to take a look at this on a graph, this is scaled a bit differently because each hash mark on the x-axis is 1 unit, while each hash mark on the y-axis is 4 units. But this is going to form a line with a slope of 2. So now if I take a look at how the quadratic function looks a bit different, notice that plugging in -2 and squaring it gives me a positive result. And I could see that the values tend to decrease until I get to 0, where 0 squared is equal to 0. But then each of the inputs or outputs beyond that are squaring the inputs to get these particular values. So if we were to take a look at that graph, that's why this graph would look like a quadratic or a parabola. So what I'd like you to focus on most is recognizing that once you get past 0 and 1 and 2, the quadratic ends up increasing much faster than the linear function. So let's take a look now at what happens with exponential functions. Notice that when you take 2 to a power that's negative, you're simply taking the reciprocal of the positive value. So 2 to the -2 power is 1 over 2 to the power of 2, which is why this is 1/4. Next, you get 2 to the power of -1, which is 1 over 2 to the power of 1, or 1/2. Now you get 2 to the power of 0. Now remember, 2 to the power of 0, or rather anything to the power of 0, is always 1. And now when you start raising to other powers, 2 to the power of 3 is 2 times 2 times 2, or 8. And you can see that these values of y get much faster, much quicker, and so are much larger, much quicker. So we should be able to see now that this graph, first of all, has no negative outputs, and there's nothing I could even plug in to make this answer 0. So what we'll notice is that going back to -infinity, there's a horizontal asymptote, but this graph tends to increase very quickly. Now, if I take a look at 2, the x value of 2, notice that no matter if I multiply 2 by 2, or if I square 2, or if I raise 2 to the power of 2, I'm always going to get the same output of 4. But once we get beyond this point here at 4, we know that the red exponential graph is going to start becoming much steeper, much faster. So in general, if we were to zoom in, we should recognize that the exponential function is going to increase much faster than the quadratic function once we get beyond a certain point. So if we now think about what exponential means, the verb exponentially, or to grow exponentially, means to change very rapidly. Like in the instance of populations growing, okay, the more humans there are, the faster the population grows. The spread of a disease, for instance, the spread of COVID, grows exponentially. It starts slow with a few people, but as more people have that disease, it increases much faster. The temperature of a heated object as it cools, if we pull a cake out of the oven, it's going to cool very quickly at the beginning, but slow down as it gets closer to room temperature. That's what we refer to as exponential growth or decay. So an exponential function will always have some base. In the prior slide, we saw the base was 2, but really this allows us to have virtually an infinite amount of parent functions that'll change based on what the base is. So if this is our standard parent function, b to the power of x, picturing b as some number, then we can see that it's going to have certain criteria in order to be an exponential function. First of all, the base must be positive. So I can't be taking a base of, say, -2 and raising that to a power of x. The base has to be positive. And secondly, the base can't be 1. Let's take a look at why the base can't be 1. If it was 1, then we would have the function f of x equals 1 to the power of x. But notice that any power of 1 is going to be 1. 1 to the power of 2, 1 to the power of 5, 1 to the power of 80. So notice that f of x equals 1 to the x is the same thing as the horizontal line f of x equals 1. So now let's think about the domain. Now you can think of the red graph that we had on the prior slide, or you can recognize that there's virtually anything that I could plug into the exponent, whether it's negative or positive or 0. So the domain is -infinity to infinity. We could pick anything we want. But as for the range, remember that the range was completely above the x-axis. The outputs for every exponential function, no matter what you plug in for x, are always going to be positive. And notice that it'll never equal 0 either. So the range is 0 to infinity, not including 0. So now let's think about what the graph is going to look like. If the base is bigger than 1, something like 2 or 3, then that would mean that we have exponential growth, where the base is positive and greater than 1. But what if the base happens to be a fraction between 0 and 1? Now we realize that we have what we call exponential decay. So exponential decay occurs when the base is somewhere between 0 and 1. Now what's important about this is that we should always get, no matter what base we have, the same exact y-intercept. Remember, y-intercepts are found by setting the x-coordinate at equal to 0. So if I plug in 0 to my exponential function, I'm going to get the value b to the power of 0. But regardless of the base, whether it's 1/2 or 5, any value to the power of 0 is always 1. So I know that 0, 1 will always be the y-intercept of every exponential. Finally, f of x will always pass through a very particular point when I plug in 1 that's indicated by whatever the base is. Because if I plug in 1 for the exponent, then any number to the power of 1 is itself. So plugging in 1 will always give me the second point I'll use on my parent function, which is the point 1 and b. Notice that as b changes, that's going to affect the steepness of the graph. Okay. Now we can see that the x-axis is a horizontal asymptote, regardless if it's exponential growth or decay. And remember that that's just indicating that it's a limiting line that the graph is going to approach but never touch. So let's take a look at a couple of different exponential functions, namely 2 to the x, 3 to the x, and 5 to the x. So if I were to graph the first function, notice that all of them are going to pass through the point 0, 1. Okay, so 0, 1 is definitely a point on all of these functions. But now we have to plot a second point for our parent function. So let's start with the graph of 2 to the power of x. If you look at 2 to the power of x, notice that I could plug in 1 to determine that f of 1 is going to give me 2. So don't think of this vertical line right here as an asymptote. It's just indicating what's going to happen when I plug in 1 for each of these separate functions. So when I plug in 1 for 2 to the x, I get the point 2. So notice that the point 1, 2 is a second point that's on my graph. But notice, what if I were to look at the graph of 3 to the power of x? Plugging in 1 is going to give me an answer of 3 now. So now, plugging in 1 gives me an answer of 3, which is higher than 2, which is causing 3 to the x to be a steeper graph than 2 to the x. And if you look at 5 to the power of x, f of 1 is equal to 5. And so notice that now plugging in 1 gives me an output of 5, which makes this graph even steeper than 3 to the x. And so we can see that the larger the base, the steeper the graph will be as it passes through the y-axis. But what if the bases happen to be fractions? So we already said that when they're fractions between 0 and 1, we know that this is going to cause exponential decay. So if we now look at each of these values, recognizing that 0, 1 is still going to be on every one of these, we could continue to plug in 1 and recognize that 1/2 to the power of 1 is going to give me 1/2. But I'd prefer not to actually plot fractions at 1, because that could get pretty tough to tell the difference between 1/2 and 1/5. So instead, we're going to use a property of exponents that tells us that if we take a fraction and raise to the power of -1, remember that that means to take the reciprocal raised to the positive power. So 1 over a raised to the -1 power is the same as the reciprocal a over 1 raised to the positive 1 power, which is really just a. So let's think about what that means. It means that if I plug in -1 to any of these functions, then f of -1 should give me the answer of 2, whatever the denominator is. So for exponential decay functions, the best way to do this is not to plug in 1 and get fractions, but plug in -1 so we could still get whole numbers. And therefore, this is how we can see exponential decay. Similarly, if we plug in -1 to 1/3 to the x, then we get an output of 3. 1/3 to the -1 is 3 over 1 to the positive 1. And that's why it's going to be a steeper exponential decay. What if we now take a look at plugging in -1 to 1/5 to the x? Now we get an answer of 5, which is again an even steeper exponential decay. So let's take a look at an example of how we can use these parent functions in order to apply transformations. So first of all, we want to graph f of x equals 2 to the power of x minus 1 minus 2. Now, if I were to start off by graphing the parent function, we should recognize that the parent function is 2 to the power of x. And remember that we have 0, 1 is on every exponential parent function. And the second point that we'll be using is always 1, 2. So we're going to plot these 2 points for our exponential and then draw our curve in order to create our parent function. Now we recognize that transformations of these types of functions work just like transformations of any other function, whether it be quadratic or absolute value or any parent function. So we should recognize that because 1 is being subtracted directly from x, this is causing me to move right 1, and subtracting 2 from the end of a function is causing me to move down 2. So we're going to take each of these individual points and shift them right 1 and down 2. If we take the y-intercept and shift right 1 and down 2, we now get this new point at 1, -1. And if we take the point at 1, 2 and shift it right 1 and down 2, we get the new point at 2, 0. Now we would normally be ready to draw the same graph. We could see the same shape in blue is going to be the shape in red. But we have to understand something else. Right now, the x-axis is serving as our horizontal asymptote. So because the x-axis is already a drawn line, we didn't have to draw an extra horizontal asymptote. But if I move this graph up or down, that's going to also move the horizontal asymptote. So we have to now draw a dotted line that represents the horizontal asymptote that moved 2 units down. Now that we have the horizontal asymptote and 2 of our new points, we can draw the new graph, and this is the new graph of f of x. So exponential functions are nothing more than just a new shape, a new type of parent function that we're still going to be applying transformations in very similar ways to what we did before. But now exponential functions have some new features and some new characteristics that we haven't necessarily seen on prior functions. Now, one thing we want to take a look at here is a new type of base called a base E. Now, I know that sounds a little peculiar to have a base that's a letter, but this shouldn't be too surprising when we start to look at what E represents. So there's a lot of application problems in this world that require us to use an exponential function where the base is this irrational number. Now I know that many have already heard of pi. Pi is an irrational number that has to do with the circumference of a circle in comparison to its diameter. And we've probably memorized that the value of pi is approximately 3.14. But it's actually this irrational number that never ends. It has an infinite number of decimal places. So we use this symbol of pi, or this Greek letter, to represent an actual number. Well, now we're looking at the value of e. When we look at the value of e, we see that it's approximately this number, 2.718, and so on, with an infinite number of decimal places. We approximate e with 2.718. So when we look at e as an irrational number, we're going to see some applications that involve this letter when we're dealing with growth and decay of populations and bank accounts and spreads of a disease and so on. So when we look at the function e to the power of x, we refer to that as the natural exponential function. It's a very special exponential function, and it's going to be graphed the exact same way as any other exponential function. So let's take a look at how we do that. We're going to plug in 0 to get 1, which makes sense because that's going to be our y-intercept. But the second point that we plug in is going to be, or the second x value will be 1. And notice the output will be e to the power of 1, or approximately 2.718. So let's look at this on a graph. Remember that 2 to the power of x is always going to have the point 0, 1. And now we just have to plot the point 1, 2, and 1, 3 to indicate the steepness of 2 to the x and 3 to the x. So when we look at both of those graphs, we can see that 3 to the x is obviously steeper than 2 to the x. But what about e to the x? Now when I plug in 1, I get the power, or e to the power of 1, which is approximately 2.718. So now plugging in 1 gives me this value at approximately 2.718. So I should see that the graph of e to the x is somewhere between the graphs of 2 to the x and 3 to the x. So graphing this type of function doesn't change anything. The only difference is that we see this base that looks like it's a letter, that looks like it's a variable, but we just have to recognize that e stands for that number 2.718. So if we take a look at the slopes passing through the y-intercept, this is going to be something that indicates why e is so important. And we actually see a lot more about the graph of e to the x, and about what the value of e means when we take calculus. But let's just go ahead and take a look at the slopes of the graph as we move through the y-intercept. What we should recognize about this one is that the slope is less than 1, because remember, slope is rise over run. And so rise over run would end up taking me through a point at the point 1, 2. Notice that this slope is less than 1. If you take a look at the graph of 3 to the x, now again, that's not going to be the slope of 1. It's a slope that's greater than 1. But if we look at the slope of e to the x, we should recognize that this is exactly a slope of 1 as it passes through the y-intercept, because notice that the rise over run is exactly 1 unit. So this is actually one thing that makes e to the x such a special function as we move forward into future math classes. But as of right now, we just want to take a look at the fact that e is approximately 2.718. So when we look at one common application of exponential functions, we can see that our money grows exponentially when we put it into some bank account or some sort of fund that's going to accumulate interest. We call that compound interest. Because if you picture what's happening with your money, you put your money into an account and each month it's going to gain interest. But now that interest is your money. So your bank account has more money than it did the previous month. So now the next month, you're going to be accumulating interest not only on the original principal that you put in, but on the interest that you just gained the prior month. And as years go by, you're gaining interest on top of interest on top of interest, and your money will continue to grow, not linearly, not quadratically, but exponentially. So let's take a look at the graph, or I'm sorry, the formula for exponential growth for compound interest. Okay, so notice the compound interest is going to be interest gained on top of the accumulated interest. So this seems like a pretty complicated formula, but the reason why this is an exponential function is because it's got variables in the exponent. So each of these quantities stands for a certain amount or a certain quantity. A stands for the account balance. So at any moment in time, maybe 3 years after you've put some money in, this is the account balance currently. You take a look at P, P stands for principal. The principal is the original amount that you invested or the original amount that you deposited. If you take a look at R, R stands for the annual interest rate. So if it says that there's an APR of 6%, that means that every year you're going to get 6% of whatever your original principal was. But in this formula, we need to make sure that we're always putting the percentage as a decimal. So 6% would actually be 0.06. If you now take a look at N, N represents the number of times that the bank chooses to compound your money. In other words, how often are they accumulating interest on top of interest on top of interest? So we refer to that as the number of compounds per year. And lastly, if you take a look at the variable t, t stands for time, typically the time in years. So how many years have you been investing? And therefore t is the number of years. So now that we have this formula and we understand what each variable stands for, let's look at an example or an application of this. So let's just assume that unfortunately after your grandmother's death, you inherited $5,000 from her when you were 20 years old. Now, instead of spending it like you may want to do, I'm going to show you why it might be a better choice for you to invest that money. So suppose you invested in an account that earns 8.75%. Okay. Well, that would be R, that would be my interest rate. Now let's say that it's compounded daily. That's a pretty standard thing for a bank to do, is that every day they're going to compound your money. Now maybe you're only getting a penny or two at the beginning, but remember that that's your penny. That's your 2 cents, 3 cents. And so that's going to accumulate over and over and over every single day. So eventually that money is going to accumulate much faster. And now we'd like to know, how much money would you have by the time you want to retire at age 65? Well, before we can do anything, we have to start stipulating what values we have and what values we're trying to find. So the first thing we should recognize is that our principal is $5,000. Next, we should recognize that our interest rate is 8.75%. So that means that R as a decimal is 0.0875. It's important not to say 0.875 or else that would be 87.5%. Then it says it's compounded daily. That would mean that N is equal to 365, because remember that the N value is the number of compounds per year. And lastly, T, the number of years invested. Well, it doesn't say it directly, but it says that you got the money when you were 20 years old and you want to retire at age 65. So that would mean that T is 45. So now that we have that, we could just find the account balance, which is A, and that's what it's asking me for. What's my account balance after I invest $5,000 at 8.75% interest, compounded daily for 45 years? And now it's a matter of just applying the order of operations. So let's start off by taking 0.0875 divided by 365 on your calculator. And if I add 1, I now get 1 point this decimal. Now we're going to write quite a few decimal places here, because we should realize that now our exponent is 365 times 45. Notice what that represents. That's the total number of days in 45 years. So our exponent is 16,425. That's the total number of compounds. So if I truncate this decimal at 1.0002, I'm going to be off by quite a few dollars by the time I end up finishing this problem. So the order of operations says next to apply the exponent. So you use your calculator to raise this to the power to get 5,000 times 51.265 and so on. Notice what this number indicates now. It tells me that within 45 years, your original principal of $5,000 will be 51 times bigger. So if you invested this $5,000 after your grandmother's death at 20 years old, and you decided to just let it wait until you retired at age 65, that that $5,000 would become $256,000, $329.97 by the time you're ready to retire. This is what we're talking about with exponential growth. Over small time spans, your money's not going to grow very fast, as you can see from the graph. But as the x value or the time increases, moving to the right, your graph is getting much, much steeper at a much faster rate. So notice that if this is the case, if the interest happens to be compounded continuously now, which is actually what a lot of banking institutions do, then that means that you're not getting paid monthly, or you're not compounding monthly. It's not compounding weekly or daily. It's not even compounding hourly or by the second. It's compounding continuously. And we can only do this because a computer is able to actually compound your money at a continuous rate. And so it actually turns out that there's an infinite number of compounds every year. So what that needs is a new formula for continuously compounded interest. And this new formula has to do with E. We refer to this as the law of natural growth. And it turns out that most financial institutions are using this formula. And so that E, again, stands for 2.718. And now notice the only value or the only variable that's not part of this formula is N for the number of compounds. Because we don't want to plug in infinity into our original formula, or else we won't be able to really find that value. So let's now look at this as the law of natural growth. And not only does it have to do with your money increasing, but this is actually the same formula for calculating the growth of populations over small time periods. It's also the formula used for radioactive decay of organisms, for learning retention, for how quickly you remember facts and forget facts, for the spread of a disease. This law of natural growth involving the number E is seen in all kinds of applications. So let's take a look at an example then involving the law of natural growth by looking at how it affects it compounding continuously. So assume you choose to invest $600 from graduation gifts in an account that accumulates interest at an annual interest rate of 4.2%. So we should recognize that R is now 0.042. And now it says that we're compounding continuously. That means we're not using that original formula that we did in our prior example. We're now using the formula that A is equal to P times E to the RT. So it says, how much money would you have in your account at the end of the first year? That means that we're going to plug in T equal to 1. And then it says, what about 18 years later? So then we would allow T to be 18. So if I use this formula for P times E to the RT, we just simply replace P with 600. E stays E because there's a button on your calculator that says E to a power. You could also recognize that that's 2.718, but it's actually not. That's only the first 3 decimal places. There's an infinite number of decimal places, so allow your calculator to use the actual value. R is 0.042, and T is equal to 1. We can now calculate the exponent by multiplying by 1, and E to this power is 1.042894479. When you now multiply that by 600, we can now recognize that this is more than 4.2%. 4.2% would mean that it's truncated right after the 2. But notice that we're actually getting more than 4.2% annually, because this is 4.2% on the interest that has been accumulated throughout the year. So if 4.2% is called the APR, or the annual percentage rate, then 4.289447 is considered the annual percentage yield, or the APY, what I actually get in my bank account. When I now multiply that by 600, within the first year, I've gained $25.74 in interest. Now, it might not seem like a whole lot, right? Because if I were to say $625.74, I've only gained $25.74 in a year. So notice that if you were to gain only $25.74 worth of interest in the first year, you might expect that the amount of interest you gain after 18 years is just 18 times that amount. So notice, let's see what 18 times that $25 is. That means that you might expect to gain $463 or so after 18 years. Turns out that you don't, though, because this is exponential growth. So you're continuing to get interest on top of the interest that you're already gaining. So let's redo this problem from the beginning and see what happens when we replace the t value with 18 instead. So now notice that instead of t equaling 1, t is equal to 18. We now calculate e to that power, which is 0.756 now. On our calculator, that becomes 600 times 2.1297. When you finally multiply by 600, you get $1,277. Notice that that's over $600 increase. I have more than doubled my original principal, which is way more than what I would have gotten if I just took $25 for 18 years. So notice that exponential growth allows our money over the short term to grow relatively slow, but if you leave it in there for a much longer time span, we know that it's going to grow at a much faster rate.